In week one, we considered the overall Earth's budget and the energy that we receive from the sun. We considered this both on a kind of collective or global scale from an astronomical perspective, and we also briefly considered this from a local perspective by looking at the Earth's relative position with respect to sunrise, sunset, and the path that the sun appears to take as the Earth rotates. In this week, what we want to do is look at the overall energy budget for the Earth and see how that energy that the Earth receives from the sun is partitioned in some key ways. And it turns out that this is extremely interesting and has some fascinating feedbacks. If you recall, the energy perpendicular to the beam external to the Earth's atmosphere is about 1370 watts per square meter, but because of the Earth's shape, half of it is in shadow and half of it is in the sunlight, and that sunlit portion is stretched over this spherical shape. It turns out that the average at the Earth's outer atmosphere is only about a quarter of that 1370 or 342 watts per square meter. But even that experience is quite a complicated fate. The 342 watts per square meter, about 77 watts per square meter are on average reflected from clouds and from the atmosphere. There is only a reduced portion, therefore, that gets to the Earth's surface, and of that, about 30 watts per square meter is reflected from things like snow-lit surfaces, from water surfaces, and from various other reflective surfaces. In addition, a portion of the photons are absorbed by the atmosphere and don't penetrate or reflect, and these photons result in an energy interception amount of about 67 watts per square meter. So although this 342 is significantly reduced from the original amount of 1370, the amount that actually reaches the Earth's surface is more like 168 watts per square meter. And that's not very much. It's not actually enough to keep a planet very warm. There is a total amount then that's reflected or that leaves the Earth's atmosphere is reflected, or photons that are sort of rejected from the planet, of almost 107 watts per square meter. And the remainder are absorbed in some way, either at the Earth's surface or in the Earth's atmosphere. The thing that's fascinating about this, though, is that the Earth actually radiates photons back up from Earth's surface at a rate of about 390 watts per square meter. And if you're thinking about an Earth's energy budget, this input of 168 with an outflow of 390 watts per square meter results in a considerable puzzle. Why is the outflow so much greater than the inflow? Surely the Earth can't sustain it. Does that mean the Earth is cooling off, or does it mean that there is a considerable source of internal heat flow? Well, there is some internal heat flow, but it's not nearly enough to make up for this difference of almost over 200 watts per square meter. In fact, the interesting aspect is that this outgoing radiation at a higher wavelength than the incoming radiation, in fact, we often call this shortwave radiation, and this long-wave radiation doesn't just simply exit the Earth's atmosphere, but experiences a much more complicated and interesting fate. There is a portion of it that actually does escape directly out into space from this original beam, but of the 390 watts per square meter, only about 40 watts per square meter escapes through that atmospheric window. In fact, a whopping 350 watts per square meter, or a very significant fraction of this original 390, is intercepted by the atmosphere itself. It's intercepted by various aerosols, in particular by clouds. And some of that is emitted by the atmosphere and will, of course, join the outgoing portions. But a significant portion of this actually radiates back to the surface. And this back radiation that is absorbed adds to the incoming solar radiation and produces a net amount, which is enough to account for the surface radiation. The total amount that we're losing through this atmospheric window plus the re-emission portions is approximately 235 watts per square meter on an average planetary basis. If you add these up, and we'll do that in a minute, it turns out that we haven't accounted for everything yet. There's a couple other transfer processes that are extremely important. Not only does energy transfer from the surface of the Earth in the form of photons, but the surface transfer also induces a mass transfer process as well. And when we have a warm surface, the warm surface creates convective cells, which will turn out to be our major topic of week 3. And these warm and rise and cause a net heating effect of about 24 watts per square meter associated with that warming of the atmosphere from direct contact. And in addition, there is a cooling that takes place of the Earth's surface of about 78 watts per square meter that takes place because of evaporation and transpiration processes. This is the combined evapotranspiration and represents a total planetary average of about 78 watts per square meter. In order to see whether this overall picture balances, we can focus on a few of the individual components of this. If we look specifically at the atmosphere as a whole, or as the Earth as a whole, I should say, we have an outgoing amount of 235 as a result of the long-wave radiation, a reflected solar radiation amount of 107 watts per square meter, and these do in fact add up to the 342 watts per square meter that is incoming. And that means that the Earth is close to balanced. The Earth, in fact, receives high-energy photons and more or less is a kind of exchange machine. From the Earth leaves a much larger number of low-energy photons, resulting in this overall transfer rate of 235 watts per square meter. But the overall balance is pretty good, and this means that the Earth is not changing rapidly. Of course, global warming is an issue that is of concern, but the global warming is still relatively slow and is a relatively small amount that's stored relative to these total amount of energy transfers, or these flux rates. If we look at the atmosphere, we have a similar balance that we can calculate. We have a certain amount of energy that comes in. We have energy that leaves in the form of low frequency photons, and we have a certain amount that's absorbed from the atmospheric portion and a certain amount that gets there because of surface transfer processes. And again, we have an overall balance. If we add up all the incoming arrows with all the outgoing arrows, actually all the outgoing arrows are here and all the incoming arrows are here, we end up with an overall balance that in fact again is roughly in equilibrium, which means that the storage amounts are relatively small. Finally, we can do the similar balance for the surface where the main inputs are from this reflected amount or this re-emitted amount and this amount that receives from the Earth, and then the outgoing amounts of the 390 plus the 24 and 78. If we add all those together, we again achieve a balance. So the overall budget of the Earth is balanced, and that's as we would expect for a surface or a condition that's been in existence for a long time. Clearly there's a bias between seasons, portions of the globe that receive more or less. There's a very considerable day-night balance, but these are overall yearly averages representing that overall effects of these individual processes. We have a radiative exchange and we have some important surface transfer processes, and we're going to be looking at those in more detail in the time ahead. If the Earth were idealized and reflected that 107 amount still, it probably would change as a result of what's happening, the Earth would be a very cold place. But the Earth is not that cold a place. It's quite a very temperate place. And the reason for the difference is that profound effect of really photon recycling that's associated with the Earth's surface. A very important effect called this greenhouse effect. We can diagram that in a fairly conceptual way the following way. We can think of the original beam coming in from the Earth, and most of that portion is being absorbed from the surface. This will cause the surface to warm, and as a result of the warming it will give off radiation associated with that warm temperature, and that outgoing radiation is partly intercepted, and so it doesn't go straight into space, but in fact as it passes through the atmosphere some of it's absorbed, and the absorbed photons raise the temperature on energized portions of the atmosphere, the result of that increase in temperature, we have a transfer within the clouds or within the atmosphere, a loss of some of that towards space, but some of it is received from the surface of the Earth again. And part of the reason for this bias again is that the bottom of clouds, being lower, are actually warmer than the upper portions of clouds, and so there's a net blanket kind of effect, and we often call that clouds blanket the Earth in that particular sense. Some of these photons are lost, but of the photons that are absorbed, of course, some of them are reabsorbed and readmitted. And so we have an overall process that actually continues through a variety of cycles. Radiation is received, is warmed, warms the surface, is sent out. Some of it's reflected back or admitted back to the surface. Of this, a portion is sent out, some of it is going to be interceptive, some of it's lost, some of it's sent back. And the process continues in a process of diminishing returns, one that is very analogous to a process of reinvestment or of getting something back that you've contributed a portion to. And the overall greenhouse gas effect is really a kind of a photon recycling effect that has this profound effect of allowing the Earth to be much warmer than it would be otherwise. The mechanism that produces this is really the profound difference between the radiative properties of certain gases in the atmosphere to shortwave radiation coming from the sun and long-wave radiation coming from the Earth. And again, we can sort of conceptualize this in a fairly generic way. We have an atmosphere made up of largely nitrogen, about 78% of a significant amount of oxygen and about 21%, a lot of argon, and then a small constituents of these greenhouse gases. Small, but they play a significant role. Roughly speaking, the greenhouse gases are made up of 5 major components, carbon dioxide being the largest of these, but a significant portion being in ozone, methane, various kinds of CFCs or chlorinated fluorocarbons, and nitrous oxide. And the effect of these in the atmosphere is precisely to capture some of the radiation that would normally be lost. If we were to redraw the picture without the greenhouse gas effect, then clearly what would happen is we would no longer get that back radiation component. As a result of that, there would be a dramatic reduction in surface temperature. Evapotranspiration would go to almost zero. The thermal processes would reduce to a very small amount compared to what they would be otherwise. And the surface radiation components would be much smaller, representing a much cooler Earth. And this would be a much less dynamic, much less interesting, and much less habitable planet than it would be otherwise. The overall sense of this is that the greenhouse gases probably induce a warming that's of the order of 17 degrees Celsius, and one that perhaps is dynamic. Human involvement is causing a change in the atmospheric composition, and it's believed that that is causing a global warming as a result of that change. It's not ever as simple as you might sometimes hope it to be. Earth's processes are influenced by humans in a variety of complex ways, including changes in land surface and the emission of aerosols, which actually cause a cooling effect as well. Again, conceptually, we can sort of think of this as a recycling process, that the escape is a complex set of exchanges that takes place. And the more greenhouse gases, the better the trapping process is, and the more the Earth will warm. Really, it's a kind of an image of almost what we get when we have a fever, that there's a warming process that takes place. Various sources of greenhouse gases include many things that humans do. Various natural processes, including things like forest fires, influence this. Natural processes uptake this, but certainly humans, with our unbelievable success in harnessing energy systems, run automobiles, factories, have a variety of human activities, of use of electricity, of use of transportation, of heating and cooling, all of which are change in the atmosphere composition, all of which might have profound implications for this atmospheric recycling process that has to do with this overall partition. Again, there's lots of places for more information. A few that you might check out are included here.